Hello everyone. I have prepared a new space journey, one that will take us to the close vicinity of Earth. We're going to talk about the possible colonization of the Moon, space mining on asteroids, and infrastructures or vehicles that would help achieve this, such as the concept of space elevator. Are all these things possible? Would they make sense? What are the technical, economic, human, or legal challenges to overcome? This is what we're going to examine. So please make yourself comfortable, and if you like this episode or this channel, take a moment to like, subscribe, or comment. The idea of establishing a permanent human presence on the Moon really started to be taken seriously in the 20th century, when it began to appear technically feasible. But as a theoretical goal, a concept, it is older than that. For example, as early as the 17th century, an English author and natural philosopher, John Wilkins, played with the idea in texts called The Discovery of a World in the Moon and A Discourse Concerning a New Planet. The idea of space travel in fiction, with the Moon as the first target for its proximity, was also developed by early science fiction authors in the 19th century. For example, Jules Verne in From the Earth to the Moon, a novel in which a gigantic gun sent a vehicle, a shell, to the Moon. But as a material process, the colonization of the Moon really began to take shape in the 1950s. We could say the process began when the first landers reached its surface. This happened under the Lunar program, a series of space missions by the Soviet Union between 1959 and 1976. It was the first program to fly by the Moon, take photos of its far side, the one that is never visible from Earth, because the Moon always shows us the same side. And in 1959, a spacecraft, a probe called Luna 2, landed on the Moon, or rather crashed on it. It had been designed to impact it rather than do a controlled landing. So the mission was a success, but the probe was destroyed. Its remains are still on the Moon. In the 1960s, the USSR and the USA were engaged in competing space programs to send manned spaceships to the Moon, a race the USA won in 1969 with the first manned landing on the Moon, the Apollo 11 mission. In 1967, the growing credibility or reality of space occupation by mankind had led to the negotiation of a treaty, the Outer Space Treaty, that forms the basis of space law. We will come back to that. The USA and USSR were some of the first countries to sign it, and nowadays more than 100 countries, including all the ones with significant space programs, are part of this treaty. It defines the Moon and all outer space as the province of all mankind, which restricts the appropriation of the Moon by any country or private organization. Theoretically or legally, the use of the Moon is supposed to be restricted to peaceful purposes, and military installations or weaponry are banned from its surface. The aftermath of the Luna and Apollo missions was a bit underwhelming in the 1970s and 80s. Once the goal of walking on the Moon was achieved and its surface was studied a bit more in detail, interest shifted to other bodies, budgets were cut, then the Soviet Union collapsed, putting an end to the space race, and the plans for human bases or the colonization of space were scaled down or scrapped. A direction that was preferred was the creation of orbital labs and stations. Not that discoveries stopped entirely. Things like the presence of water ice on the Moon were discovered later. But until recently, projects to establish a permanent human presence on the Moon were deemed not justified enough. Too expensive, too complicated for the scientific or economic dividends it could yield. The interest is now back, and we're going to talk about it and how it could be achieved. But first, establishing permanent human settlements in other places than Earth faces a huge constraint: the complexity and cost of regularly sending crews, supplies, and building materials into space. As you know, rockets contain mostly fuel. Their payload is only a fraction of their weight. And even when parts or vehicles can be retrieved and reused, such as space shuttles or the reusable rockets that have been in development for the past few years, the cost of sending a ton of material, equipment, water, air, food, building parts into space is tremendous. And this seems to make the colonization of space impossible if human crews in space or on other bodies than Earth depend entirely on rockets launched from the Earth's surface. How to find and use resources in space without having to process them on Earth, and how to send up there big quantities of material at a reasonable cost. One compatible with the building and survival of out-of-Earth bases with more than a handful of astronauts, like what exists today with the International Space Station. This is when concepts like the space elevator and space mining become relevant. What are these, and are they credible? The space elevator, also called orbital lift or space bridge, would be a transportation system connecting the surface of a planet and a station, a counterweight, placed at or beyond geostationary orbit. That is to say, far enough from the planet to not fall down onto it due to gravitation. Imagine a cable anchored on Earth near the equator and extending all the way up to a station that always flies at the vertical of the place where the cable starts. How far from the surface? In the case of Earth, the geostationary orbit is about 36,000 kilometers, 22,000 miles. For comparison, commercial flights typically fly at an altitude of 10 kilometers, or 6-7 miles. So we're speaking of 3,600 times higher. Also for comparison, the cable would be close in length to the circumference of Earth. The circumference of Earth is 40,000 kilometers, or 25,000 miles. And still theoretically, the system could work because it would be subject to two competing forces. First, there would be gravity pulling the cable towards the surface, a force stronger at the lower end of the cable where it is closer to Earth. But second, there would be the centrifugal force, as the counterweight in orbit would be traveling very fast in space, following the rotation of Earth. At the equator, Earth does one rotation in 24 hours, so a given point moves 40,000 kilometers in 24 hours. That's close to 1,700 kilometers or 1,000 miles per hour. Of course, we can't feel it, because our reference is the Earth's surface, but relative to the center of the planet, we are moving constantly and quickly. Now, an object in geostationary orbit that remains at the vertical of a point on Earth has to travel way faster than that. Its orbit forms a bigger circle around the planet because it is far from the surface. And in that case, the speed is roughly 11,000 kilometers per hour, 3 kilometers or 2 miles per second. This implies a powerful centrifugal force that would pull the top of the system, the counterweight, and the upper end of the cable away from Earth. The equilibrium of these two forces, gravitational and centrifugal, would keep the counterweight stationary over the same position on Earth, and the cable under tension. With this bridge stabilized, connecting the surface to the orbit, it would be possible to send vehicles, elevators or climbers, climbing up and down the cable to bring cargo and people up and down without the need of rockets. The theory is easy to understand, conceptually it is appealing, and that's why the concept of space elevator has appeared in sci-fi for decades. But of course in practice it would not be that simple. The type of materials needed to resist the constraints, the building from the anchorage to the counterweight in space, the risks, because what if something goes wrong and a huge cable as long as the Earth's circumference, or longer, and weighing millions of tons, falls back on the planet. That's a lot of challenges, starting with the exact dimensions of the space elevator. I told you the counterweight needed to be at least in geostationary orbit, far enough for gravity to be weak enough so that it doesn't crash on Earth. But that's a minimum distance. An equilibrium has to be found between the gravitational and centrifugal forces, and that will depend on the mass of the cable and the distance, how far the counterweight is positioned. In practice, it could have to be placed thousands of miles beyond geostationary orbit, depending on the characteristics of the elevator, how thick the cable is, and what it is made of. So there are challenges of different types. Materials, what could it be made of, taking into account resistance to not break under the tension, and weight. Construction, how do we place this massive counterweight and deploy this gigantic cable? Maintenance, what if space debris or asteroids hit it? And obviously there's the cost. Does it even make sense against the alternative of rockets? The space elevator concept was first imagined more than a century ago and written about by different authors, at the beginning more sci-fi authors than actual space engineers. But in the past few decades, the possibility of building it has been studied and discussed more in depth by scientists. The design with a counterweight and a cable emerged in the 1970s. Prior to it, the ideas were closer to towers that would not extend as far as outer space, but that don't really seem realistic at all, for a variety of reasons, starting with the foundations of such a tower. Even if the foundations were several miles deep into the Earth's crust, that would still be negligible for a height of thousands of miles or kilometers. It doesn't work because no conceivable foundations seem able to avoid the tower sinking or crumbling. For comparison, you know about these very slender modern towers, like the ones of Billionaires Row in Manhattan. The most extreme of these towers, when it comes to the ratio of its height relative to its base, is the Steinway Tower. It is 1,400 feet high, that's 435 meters, with a width at the base of 59 feet, 18 meters. This gives a ratio of 1 to 24. The tower is 24 times higher than it is wide. If we were to build a tower of similar proportions, whose top would be in low orbit, where many commercial and weather satellites are, they are not geostationary. They will eventually fall back, or they would if they were not regularly moved away. So a tower reaching low orbit would be the absolute minimum, and it would have to rise to at least 500 kilometers, 320 miles. If we apply the 1 to 24 ratio to such a tower, the base would have to be 20 kilometers wide, about 13 miles. So the side of the base would be about the length of Manhattan, north to south. And let's not speak of a tower reaching a geostationary orbit at 36,000 kilometers. Still with the same ratio, its side would need to be about 1,500 kilometers, almost 1,000 miles. That's about twice the length of Florida, 4.5 times the distance between Paris and London, or almost 3 times the distance between San Francisco and Los Angeles. Even if building foundations was possible, and it's not, we're never going to build a tower with such dimensions. So only the cable and counterweight system seems to have at least theoretical feasibility. And that raises the question of what the elevator could be made of. A type of material that would be strong enough to hold its own weight, the constraints, with high gravity at the base and high centrifugal force at the top, plus the payloads that would climb up and down. To minimize weight and not have to place the counterweight too far away, the cable would probably have to be thinner near the ground and thicker at a geostationary orbit and beyond. This would mean more mass in altitude, so less need to place the counterweight far beyond geostationary orbit. Based on current calculations, no metal available or alloy like steel is believed to be good enough. They are all too heavy relative to their strength, their resistance to tension. There are high-performance fibers, composite materials such as Kevlar, that combine high strength for a limited weight. And actually, still based on estimates, this necessary equilibrium between gravity and centrifugal force it seems that Kevlar could be good enough for space elevator cables on smaller bodies than Earth, like the Moon or maybe Mars. Bodies that have less gravitational pull due to their smaller mass, so they require a lesser strength-to-density ratio for the cable. By the way, in this context, space cables are also called tethers, if you see the term. A tether is a space cable. And of course there is no existing tether that would be thousands of kilometers long. But the technology exists. Several space agencies around the world have deployed some in orbit to connect two spacecrafts, for example. In the 1990s, NASA conducted missions called SEDS, SEDS, Small Expendable Deployer System, during which tethers up to 20 kilometers long, 14 miles, were deployed in space. So Kevlar, to give you orders of magnitude, is a strong synthetic fiber developed in the 1960s that is about 5 times stronger than steel when it comes to its tensile strength. In other words, a Kevlar cable can resist the same tension as a 5 times bigger steel cable. But still, Kevlar does not seem good enough for an Earth-based space elevator. And neither are the most advanced synthetic materials we currently have, such as carbon nanotubes. But that could change if we find ways to strengthen them further. Carbon nanotubes are microscopic structures made of carbon. They are very strong thanks to the strength of connections between carbon atoms. And they are called nanotubes because they are empty on a microscopic scale. The atoms are arranged in a tubular structure. Nano is because of their size. They are microscopic. A typical tube has a diameter of 0.5 to 2 nanometers. For comparison, that's 100,000 times thinner than a human hair. For greater strength, multi-walled nanotubes can be made, with nested carbon nanotubes inside slightly wider tubes. Of course, in practice, nanotubes are used in large numbers, and not just for their strength. They are also useful as semiconductors, and they are very good thermal conductors along the tube, while at the same time being good insulators lateral to the tube axis. Heat circulates well along them, but not across. So since the 1990s, when industrial processes to produce them were discovered, they have been introduced in plenty of applications, including consumer applications, like in battery components, or to improve the mechanical, thermal, and electrical properties of many products. More applications are under development in electronics, high-strength fabrics, or medicine. Again, to give you an order of magnitude of their mechanical properties, I told you Kevlar had 5 times more tensile strength than steel. For carbon nanotubes, we are talking of 100 times more strength when it comes to their resistance to tension. So a very interesting and promising type of material, which could be further perfected with even stronger nested tubes. But for the moment, this is still not good enough for an Earth-based space elevator. They would have to be perfected further, or other materials should be used, because there could be even more performing alternatives in the future. Alternatives like boron nitride nanotubes, which are similar structures but in which boron and nitrogen atoms replace carbon. Their properties are different. They are good insulators along the tube, for example, contrary to carbon nanotubes. But when it comes to tensile strength, they are comparable to carbon nanotubes today, and maybe they will turn out to be easier to reinforce further in the future. Another alternative could be diamond nanothreads. Diamond nanothreads are also made of carbon, but instead of a tube structure, they consist of a carbon core surrounded by hydrogen atoms, and that makes them thinner than carbon nanotubes. For a similar density, it is believed they could turn out to be as strong or stronger than nanotubes. This is still early stage though. Nanothreads really started to be investigated in the years 2000, and the first nanothread was created in 2014. In practice, they are still way shorter than carbon nanotubes. The longest nanothreads synthesized are still on a microscopic scale. So, returning to the project of a practical space elevator, the bottom line when it comes to materials is that we don't have them yet. All hopes are placed on the improvement of existing high-performance materials or the discovery of others in the years to come. That sounds uncertain, but not out of reach. Second problem after materials, there is the construction itself. Building from Earth, however we look at it, looks impossible. The cable would be way too heavy to attach it to a vehicle, a rocket presumably, that would take off from the surface to unroll it, to spool it. It is not possible to estimate this weight without knowing what it would be made of and its dimensions. But we're speaking of millions of tons probably. For comparison, the heaviest payload ever sent into space by a rocket is 141 tons. This record still belongs to the Saturn V rocket, the great rocket built in the 1960s for the Apollo program. But now with this cable, we are talking of thousands of times more. It is never going to work with a rocket that takes off from Earth. So this means construction would have to take place on the other side of the elevator, in space, where, for example, a station placed on a geostationary orbit would contain a factory able to make the cable, which would then be deployed. That's complicated, but technically not unthinkable neither. In order to keep the system in orbit while the station spools out the cable, it would probably have to be moved a bit further from Earth, because as the cable would slowly descend, gravitation would pull the whole system downward. In other words, for the space elevator under construction to stay in orbit before being anchored to the ground, its center of mass would have to stay on the geostationary orbit. This means sending the station away as the cable is deployed. But if we assume such a station could be built, sending multiple payloads into space and assembling it there, with what materials is it going to be built? The building materials and the energy would have to be found out of Earth. And this is where space mining, on the Moon or asteroids, appears as a prerequisite if we ever want to build a space elevator. At least the first one. In theory, if one already exists, materials for a second or third one could be sent into space using the first one. But it doesn't solve the problem for the first ever. We're going to talk about space mining in a minute, but before that, apart from materials and construction, there are other engineering challenges. Just to mention a few, vehicles would have to be designed to climbers that could move up and down the tether, the cable. Not self-propelled, because the whole point is to save fuel and increase payloads. So one way or another, they would have to be moved with more cables, like for an elevator cabin, or by electrifying the tether. But one way or another, the climbers would have to be powered. Yet another aspect to take into account is the risks. The system needs to be risk-proof. A rupture of the cable is not acceptable. It would make a section of it fall back to Earth, with catastrophic consequences. And if it happened, the counterweight in space could escape. Unless it has its own propulsion to stay in orbit when the equilibrium between gravity and centrifugal force is suddenly broken by a rupture of the cable. But what if the cable is attacked, with a plane for example? What if meteorites cross its path and damage it? A solution in that case could be to build the cable as a large strip of material, or two strips forming a cross, rather than a cylindrical cable, so that in case of impact it wouldn't be ruptured. Small or medium objects could go through it, and it could be repaired later. But as you see, challenges are huge, and I'm not even talking about the cost. The cost would make sense only if humanity has an ambitious space colonization or space travel plan, which is not the case today, even though interest in these fields have been slightly revived in recent years. Now, I was telling you that space mining looked like a prerequisite for a space elevator, and probably also any large moon occupation project. So what is, or what would be, space mining? Like for the space elevator, it is a concept that existed in science fiction before it was seriously studied or appraised by the scientific community. After the moon landing in 1969, the idea of increased human activity in space, exploration, colonization, maybe permanent life in space, this raised questions about the resources that could be tapped into. Because despite the huge progress in spaceflight in the 1950s and 60s, it also appeared that a big limiting factor would be the cost, technical and financial, the cost of sending large payloads with rockets. So resources, including energy, would have to be gathered in space. Energy through solar panels or power plants, nuclear or otherwise, and the materials would have to be found on celestial bodies. The moon, or the satellites, the moons of Mars, for example, Phobos and Deimos, or asteroids. The density in asteroids close to Earth is low, but there are some, without having to travel as far as the asteroid belt between Mars and Jupiter. At the same period, in the 1970s and 80s, the chemical composition of asteroids and moons was a topic of research too, Prior to this period, what asteroids could be made of was very speculative. For example, a hypothesis at the time was that water may be a very rare component in the solar system and the galaxy. And it was believed that we were blessed to have some on Earth. This is a theme that passed into sci-fi, by the way. The theme of aliens coming to Earth to steal our water. That was the premise of a TV show like V in the 1980s, but also of plenty of sci-fi novels of the 50s, 60s, 70s. A premise that would no longer work today, because thanks to the progress in investigation methods like spectroscopy or the sending of probes, we now know that water is fairly abundant. There is some on the Moon. It was proven in the 90s. There is some on Mars, and even more in the asteroid belt or the moons of Jupiter and Saturn. Earth doesn't even have that much water in comparison. Nowadays we don't precisely know what asteroids contain at a distance. It remains difficult to assess without landing on them. But the presence of valuable elements is very likely, especially iron, water, that could be split up into breathable oxygen and hydrogen that can be used as fuel, probably also many rare elements. Some of these materials could not be that precious for themselves, in the sense that we have them on Earth too, where they are way easier to access. But their value would come from the fact that they are already in space. It would be tied to their location. And the concept of space mining led to the founding of the first asteroid mining companies in the 2010s. Asteroid mining with quotes, because they never mined an asteroid. They were more like engineering and research organizations, aiming at one day mining asteroids. Companies, startups like Planetary Resources in 2012 or Deep Space Industries in 2013. But they didn't really go anywhere, and a few years later they shut down or they were sold for the prototypes they had created. There is a resurgence of the concept, especially driven by SpaceX at the moment. But the history of both space mining startups and SpaceX invites to not hold our breath. It is probably not happening anytime soon. Clearly not this decade, and probably not next, beyond possible experimental missions. But longer term, it is still probably the only possibility if mankind is to colonize other places in the solar system than Earth and its close orbit. And also long term, it could be an answer to resource depletion on Earth, or accessible resource depletion. A lot of elements that human industry needs are present on Earth, but inaccessible, because during the formation process of the planet, most heavier elements, especially those that have chemical affinity with iron, were pulled towards the planet's core. They sank into it. And they left the crust almost entirely depleted of these elements. Later in the formation process, when Earth had cooled down and a crust had formed, a rain of asteroids coming from farther in the solar system would have reinfused this depleted crust with elements, especially metals, like gold, cobalt, iron, platinum, rhodium, tungsten, and more. These are the metals that are mined today. But that's interesting because the Earth and these asteroids of the asteroid belt or closer formed, accreted from the same starting materials. So smaller bodies like asteroids could be incomparably richer in rare elements than the Earth's crust. They would still contain a lot of dirt, of rocky material or frozen water, but also high concentrations of rare metals. Possible ways of exploiting them could include sending probes, vehicles that would land on them, and then use propulsion to drive them out of their orbit and move them closer to Earth or closer to the Moon, on a stable orbit where stations could process them, mine them. Otherwise they would have to be processed on site, but that would imply factory ships of a larger size, going on missions that could last years. Again, given our limited capacity for construction in space, that looks complicated. These flights would not necessarily have to be manned, they could be entirely automated. The difficulty could be the lack of human presence for troubleshooting or maintenance. And there is also the problem of communications, because given the distance, back and forth communications with Earth could take several minutes. But these communication delays did not prevent the success of robotic missions like the rovers sent to Mars. There could be way more to say about the technical aspects and feasibility of asteroid mining. But like for the space elevator, the concept feels at the same time very ambitious, costly, risky, and clearly we are not there yet. But the kind of technology required for asteroid mining is not out of reach. It is not a high-concept project that would require multiple breakthroughs to be even conceivable. Maybe the biggest challenge is the economic equation. Are we interested in investing huge amounts upfront for an uncertain result? Or will one day the depletion of critical rare materials on Earth make it the only option to find them? In any case, any permanent colonization of the Moon with a large human group would require space mining on the Moon, be it only for water. So let's now talk about this Moon colonization. How hard would it be? Is it worth it? And what could it look like? First, why? Why establish a permanent presence on the Moon, when even the more inhospitable places on Earth are way easier to live? At least they have breathable air, the temperatures are not as extreme, the radiations are limited by the Earth's magnetic field and the atmosphere. And on top of that, it is way easier to go to and leave these places. But there could still be a list of reasons that would justify a moon base. Scientific and research-related reasons, and for technological advancement that could then spread to other fields, or turning the Moon into a starting point for deep space exploration, or maybe for its resources, or, even though it sounds very theoretical, as a way of spreading risks of survival for the human species. If we were to live sustainably in different places around the solar system, the risks of seeing our species wiped out would decrease, possibly. So let's take these various reasons in order. When it comes to scientific research, it would not just be about studying the Moon itself. The location also has advantages that are not replicable on Earth. First, for space observation with radio telescopes. The far side of the Moon, the side that we never see from Earth, is shielded from Earth radio noise, all the radio waves we emit constantly that pollute our close vicinity. Having observatories on the far side of the Moon would provide one of the best spots in the solar system to observe and study the universe, with possible breakthroughs on the line. Another aspect is the low-gravity environment. Microgravity, or the absence of gravity, is an environment that can facilitate the manufacturing of materials or medicines, an environment that is hard to replicate on Earth. It is true that a space station closer to Earth would also have the same advantage. But if we need larger facilities, the Moon could be a good place to build them. Then there is the idea that the Moon could be a good first step if mankind is to colonize other places. And this could be true for various reasons. First, in order to learn how to build bases and all the systems required for their sustainability, including construction techniques, oxygen and water extraction, food production, human health, including mental health, how to protect our bodies in a low-gravity environment long-term, surrounded with radiations. A second reason why the Moon could be a good starting point is its low gravity again. Launching spaceships from it requires way less energy than from Earth, really way less. Roughly 22 times less energy for a given cargo. Why such a difference? First, of course, because the Moon is smaller, less massive, so its gravitational pull is lesser, and this results in a lower escape velocity, the speed one must reach to escape it. It is 4.7 times less than on Earth. And on top of that, the very thin atmosphere means there is barely any atmospheric drag, no frictions from the air. And this is compounded again by less fuel to carry. In rocketry, you must burn fuel to lift the weight of the remaining fuel that will burn later during the flight. That's a big reason why the mass of an Earthbound rocket consists of roughly 85 to 90% of fuel, just to put a small payload into orbit. For a large part, this fuel is burned to lift more fuel that will be tapped into later during the flight. So for all of these reasons combined, lower gravity, almost no atmospheric friction, and no need to lift fuel with more fuel, you can leave the Moon with 22 times less energy than the Earth. This would be a true game changer if ships are sent on missions to other planets. And then, when it comes to using the Moon as a base for space travel, there would be also the possibility to use it as a kind of gas station. We know it contains significant water reserves, meaning hydrogen and oxygen that could be obtained from this water and serve as fuel for rockets. A third appeal of the Moon I mentioned would be for its resources. Not that the Moon has extraordinary metal or rare material deposits, but it has something that is almost absent, incredibly rare on Earth: helium-3. What is it, and why would it be important? Helium-3 is an isotope of helium. That is to say, it is chemically helium, as any atom with two protons in its nucleus. But it also has one neutron, hence the name helium-3, 3 particles in the nucleus. The regular type of helium we have in large quantity on Earth is helium-4, with 2 protons and 2 neutrons. And this helium-4 has a low economic value, because it is relatively abundant. So why would helium-3 be more valuable? The reason is that, theoretically, it could serve as an almost perfect fuel for future fusion reactors. You know that there is intense research nowadays to try and design practical fusion reactors. None is in service yet, nor will be in the next few years. But these fusion reactors could provide one day an abundant source of clean and cheap energy. Instead of using fissile material like nuclear reactors, which generate energy but also radioactive waste and come with significant operational risk, a fusion reactor would make atoms fuse, merge, like the energy source that powers the stars. What atoms? Hydrogen. At least this is the fuel most planned fusion reactors would use. Precisely molecules of 2 hydrogen atoms, this is called deuterium, and 3 hydrogen atoms, which is called tritium. This type of fusion reactions with deuterium or tritium would be way cleaner and potentially way cheaper than nuclear reactors using mostly uranium. Hydrogen is cheap and easy to find. No need to enrich it to obtain nuclear fuel. And in case of an accident, there could be the heat of the reactor, but no risk of a major catastrophe. There is no nuclear waste created, or rather, almost no nuclear waste. Because the fusion of deuterium or tritium ejects neutrons that are not included into the fusion product. And these high-energy neutrons that travel very fast are a type of radiation that can degrade the reactor's walls and end up making them radioactive. This is where helium-3 becomes attractive. Like hydrogen, helium is a very light element. Hydrogen has 1 proton, helium has 2, and its fusion with other helium atoms or with hydrogen is also strongly exothermic. It releases energy. The energy density of the reaction is very high. An extreme amount of energy could be liberated by fusing small amounts of helium-3 if we manage to do it. To give you an order of magnitude, theoretically 100 tons of helium-3 would be sufficient to power the entire planet Earth in electricity for a full year. It is that efficient. To say the same differently, the entire USA could be powered for a day with just about 50 kilograms, 110 pounds of helium-3. That's theoretical because we can never harvest all the energy of a reaction. But even if we could get only 10% of it, that would already be a game changer. And on top of that, it could be cleaner, because the fusion of helium-3 with itself or with deuterium does not release neutrons. On top of heat, it releases protons that could be captured using magnetic fields to generate electricity directly, without steam turbines like in nuclear reactors or the fusion reactors that are currently being researched. So on paper, it could be almost like a holy grail of energy production, incredibly efficient, perfectly clean, and may be usable in small plants without the need of huge turbines to make electricity. Why is there helium-3 on the Moon and not on Earth? Because helium-3 was not, or barely, present in the primordial material that served to form the solar system. It is produced by the Sun as a product of the fusion of hydrogen, and then some of it is thrown across the solar system in solar winds. But Earth doesn't receive any, because it is shielded by its magnetic field and its dense atmosphere, leaving our planet with zero supply. Whereas not having these shields, the surface of the Moon is directly impacted by solar wind and has accumulated helium-3 for hundreds of millions of years. Helium-3 stayed trapped in the soil, in the regolith, the dust and small rocks that cover the Moon's surface. So the exploitation of helium-3 on the Moon would not look like an underground mine. It would consist in treating the soil to extract it. And the Moon may be a rare source of accessible helium-3 in the solar system, because there are not that many places that could have accumulated so much of it. Venus has a very dense atmosphere. Mars has a lighter atmosphere, but its surface has experienced erosion by winds, geological activity, heavy oxidation of the surface. All of these factors prevent a light gas like helium-3 to tightly bind to the soil like on the Moon. Now, even on the Moon, where there is a lot of helium-3 comparatively, it is still present in very low concentrations in the soil, about 10 to 20 parts per billion. This means that in order to extract 1 ton of helium-3, we could have to process almost 100 million tons of lunar soil. The processing would consist in heating this lunar soil to roughly 600 degrees Celsius, which releases the trapped gas from its mineral matrix. But that would require a massive infrastructure. We are not speaking of a base with labs, but rather entire factories and vehicles bringing thousands of tons of soil for treatment every day. That's how complicated it would be. What could still make it economically viable would be the value of this helium-3. In total, there would be more than 1 million tons on the Moon, enough to power mankind on Earth for thousands of years at our current electricity consumption. It is very theoretical, but based on current energy prices, 1 ton of helium-3 could be worth $3 to $5 billion. It would have to be brought back to Earth, consumed in reactors that do not exist yet, and if it worked, the price of energy would certainly end up falling. That's the point. But even if it is only partially true, the value of helium-3 on the Moon could justify the gigantic investments to colonize it, and maybe also build the space elevator we discussed before, because helium-3 would have to be brought to Earth. So if there is this potential treasure on the Moon, this raises the question of who would own it, legal or power issues. I told you at the beginning that the Outer Space Treaty of 1967 was still valid, meaning that for the moment these resources belong to everyone or no one in particular. There was a Moon Agreement another international treaty started in 1979, but it is not very relevant because only 17 states worldwide are parties to the treaty. And of the 3 countries that currently have self-launched human spaceflight capabilities, the USA, Russia, and China, none has signed it. Even though the prospects of exploiting space resources are still rather theoretical, in 2020 there was an American presidential executive order that explicitly said the USA does not view outer space as a global commons. Nothing too intense at this point, but that seems to anticipate on the possibility of exploitation of space resources by states that can do it, or private interests maybe in the future. In any case, if prospects for space mining or moon mining take shape in the next few decades, there is probably going to be tension around it. It could become a new Far West, as governments or companies rush to appropriate resources. It remains very theoretical at this point. The 1967 treaty is still in force, and it may be a bit early to worry about large-scale exploitation of asteroids, the moon, or the building of space elevators when we don't even have the technology to achieve these things yet. And the funding would remain a huge problem. Here again, for comparison, the order of magnitude we would be talking about would be well above the current investment rush into AI, one that is already challenging to fund. Apart from helium-3, the other critical resource any large lunar base would need would be water, and for decades the question of whether there was water on the moon remained open. The scientific community is now confident that yes, there is water, especially at the North Pole, where an estimated 600 million tons of water ice in sheets could be accessed rather easily. But not only there, water seems to be locked up in minerals relatively close to the surface and possibly present in larger sheets in depth. So the plan for a possible lunar base would be to look for a place where a basic structure could be installed, domes, for example, brought from Earth, from where pioneers would build a base underground, or at least partially underground. A big challenge to long-term survival would be radiation. There is no magnetic or atmospheric shield, so radiation levels that are way too high for human health reach the surface constantly, and sometimes there are bursts of solar radiation that could be deadly. So protective buildings, or even better underground facilities, could provide protection. A few meters of material can effectively block most of radiation. On this base, the priority would be to find a source of water, of ice, given the temperature, from which drinkable water and oxygen and fuel based on hydrogen could be produced. Energy supply could come from solar panels, at least at the beginning, but for larger bases or manufacturing activity, a power plant, nuclear or ideally fusion reactors would certainly be necessary. If such a base is to become larger, it will need a lot of building material, and the moon could provide them. There are iron, titanium, aluminium or silicon deposits, precious metals and rare earths too, not in quantities and ease of access that would justify mining them to send them to Earth, but locally they could be processed in order to expand lunar facilities. Or they could be a source of building materials for a possible space elevator around Earth. As I said before, it takes 22 times less energy to take off from the Moon, so it could make sense to send them to the geostationary orbit around Earth and use them to build the elevator. Technically, the development of such a base would be very ambitious, a complex and very costly endeavor, but there is no technical blockage right now. All the technology necessary is already available: propulsion, materials, electronics, communications. What could be trickier would be for such a base to produce its own food. It looks doable with plants, algae, fungi, but that would require large underground facilities, a lot of energy, and it comes down to the reasons to do it. There could be these scientific benefits and the positive externalities of such a project, meaning it would push innovations that could then benefit many other industrial applications. But we are still quite far from being able to use helium-3 in a reactor. And if the idea is to use the Moon as a base, a launch pad for space travel around the solar system, to Mars in particular, we don't really have detailed plans for that either. So it is probably reasonable to expect that if it happens, it's going to be slow and very progressive, the first step being a planned return to the Moon in 2027. There would be many more things to say about space colonization, but for now, we have reached the end of our episode. If you are not sleepy yet, you may pick another story in my library and embark on another journey. Or you may close your eyes, let go, and fall asleep. I'll be back soon with a new story, and in the meantime, sleep well, sweet dreams, au revoir.